Okay, we're going to continue that problem we left off with in lab the other day, but were there any questions? Uh-huh.
Can you kind of explain the difference between KEQ and KC?
KEQ and KC, it might be the same, it might be different. KC is all just the concentrations. KEQ are the activities. And it depends. If it's a solution, then the activity is the concentration. But if it's a gas, then the activity is the pressure. And so it might be the same, it might not be the same. It varies depending on what we're looking at. Uh-huh.
Yeah, I thought on the calculator, both sides are slightly different.
5.63.
10 to the 5th.
5.63 times 10 to the 5th.
Yeah.
What did you get for the Kelvin?
457.13.
Yeah.
Or what did you get for temp?
I just decided to add like the 0.13 since you could just add it to 73.15 or 13.
457 you got? Okay. And 1.48 times 10, and then you use 0.0821?
Yeah.
I don't know. There's something wrong. That's right. No. There's something wrong with the book's answer. But the setup is right, so you should be right. All right. You have to look at it case by case. Case by there's no general relationship. Yeah. It's basically. Can you repeat the question again?
For KP,
Mm-hmm.
It's a partial pressure of the reactor output. But then, like in the homework, I saw some KPs they use molarity.
No.
No.
Which one? Do you know which one? No, they would use it for KE2. They could use molarities and partial pressures. I mean, if you have something like this, calcium carbonate, solid plus 2HCl, it goes to H2O liquid plus CO2 gas plus calcium chloride.
So like if they give you the KP and they also give you the molarity of like for one of the elements, then do you have to convert it to partial pressure like HCl atmosphere? Like for example, if they give you like HCl equal to 0.1 molarity, but they also give you the KP. So when you do
They aren't going to give you the KP because KP doesn't work for this equation.
I mean, like,
they give you the pressure of CO2? Yeah. Then let's say, for example, if they give you the molarity and the partial pressure of the CO2, then you would need the molarity of calcium chloride. Then we could do a KEQ for this. The KEQ would be equal to, the partial pressure of CO2 times the concentration of calcium chloride divided by the concentration of HCl squared. That would be the KEQ. Now, the partial pressure of CO2 would be either bar or atmospheres, but this whole thing would not have any units. We don't include units in this because the activities are dimensionless. You thought of the unit there. Now, there are some complications. Like, for example, there's one problem we spent some time last night working on. One from the other class had a question on this. Particular problem.
Actually, are you guys aware that I'm doing these homework sections? Not all of them, but a lot of the problems. We covered.
Like Thursday night or Friday night, but I didn't know until Sunday that you've been doing them almost every night.
Yeah, just because there's a lot of homework problems. Sorry if you missed that. But this is going to be ongoing. So tonight there's going to be another one. You know, if you want. I'm going to just finish all the problems. But last night we talked about. Oh, this thing keeps popping out. I'm going to get rid of this. Read and write. Do you know about read and write? This extension, is it required? Okay, I'm going to stop using it. Well, anyway, there was one problem. Let me show it to you. Or you could just, the videos, let me just repeat what I said. So I have these, just going through nightly sessions. They're all recorded, so you can watch the recording as well. Yesterday's I haven't posted it, but there'll be a recording.
I tried watching one yesterday. It said it was 2 hours, but it cut off like halfway through. And it just stopped.
It just stopped?
Yeah.
Oh. Well, that's weird. And they're all around 2 hours. Yeah.
They're all about around halfway for me.
Okay, well, let me take a look at that. Let's see. Just a moment here. This one here. This one's more complicated because, this is a KC. It's a KC, but we have both a gas and an aqueous solution. And this one's really complicated because the concentration, they're in different volumes. So the gas is in one part of the container and the solution is in another part of the container. And so we can't just set up our ice table as normal for number 76. So 76 was a tough one. Hopefully that one, the recording worked okay because it took some time to go through. Let me just take a look at the recording. guess, Mike, this isn't working either. So I'll check the videos later and see what happened to those. But we take it case by case. So, KC is just all concentrations. And KC, you're going to be limited to what you can do with a KC to certain reactions. Oh my. We'll come back to that in the videos. All right, for right now, let me take a look at the problem that we were working on last time. And that was the pH of 1 times 10 to the minus 8 molar HCl. HCl is a strong acid. Strong acids dissociate, ionize, or hydrolyze completely. So if that's the case, then HCl consists of the ions H plus and Cl minus. And so that means this is going to equal 1 times 10 to the minus 8 molar H plus. And the pH is equal to the negative log of the H plus concentration or the hydronium. H plus and hydronium I use interchangeably. And so the power of the H is 8, and then how many sig figs? We have 1 sig fig, so the pH comes out to 8.0. But that's a problem. What was the problem with this pH?
Too high.
Yeah, it's too high. This is the base. This is a strong acid, so it's wrong. This pH is wrong. It's wrong because I'm not taking into consideration there's more than one source of hydronium or H plus. And the sources of hydronium in this are going to be from HCl, and the other source is going to be from water. But water is such a small contributor, most of the time we ignore it. However, in this case, we can't ignore it. And so how we do this is what we call multiple equilibrium. And so this is wrong because H2O in this particular problem will be a significant contributor. And the way we can figure out what the contribution from H2O is by using Kw. And so this is what we call a multiple equilibrium problem. We're dealing with multiple equilibria, whether there's multiple equations. And what are the methods to solve multiple equilibria? The first method is the way we're going to solve this problem is stepwise. In stepwise, you start off with the strongest contributor, which would be the strongest acid, HCl, and then you work your way down. H2O would be weaker. And so step 1 is the strongest, in this case acid or strongest species, and then step 2 would be weaker, etc. We could have step 3, step 4, step 5. Stepwise is good because this is easier than the next method. The next method is simultaneous. This is harder. The situation with the simultaneous is it works for everything. And so it works, always works. Stepwise sometimes fails. And we'll talk about when it fails, how to recognize when it fails. The third method that we use is we solve them independently. That is, there's nothing in common between one reaction and another reaction. That is, there's no common species. Like, for example, common ions. But they don't have to be ions. Therefore, they're independent of one another. And the fourth method is combined. But combined sometimes fails. In fact, combined only works for one specific scenario. And so I should say not sometimes. Combined sometimes works. Most of the time fails. So let's take a look at how we would do this stepwise. So when we do the HCl, we're going to do the biggest contributor of hydronium first, or the strongest acid. In this case, the strongest acid would be HCl. Would react with H2O, it's going to form hydronium. This will be my step one. We know that strong acids are strong electrolytes. Strong electrolytes completely ionize or completely hydrolyze water. And so this is complete hydrolysis here. We could look at the K for this. The K for this is going to get this little subscript A. And what Ka is the acid ionization or the acid hydrolysis constant. Most of the time it's called the acid ionization constant. All Ka is it's just the same thing as Kc. Except we know when we see Ka, it's acid plus water. And so Ka means acid plus water. And that's what we have here. We have acid, HCl plus water. Now, the Ka for this is given as literally very large. And so if we look at the chart over here in the middle of the room, we can find HCl up here. And then the Kas are to the right here. If we look at the Ka for this, it's literally very large. And so what does that mean? Well, that means we have 100% reaction. In other words, complete reaction or complete ionization. And then complete ionization / hydrolysis. 100% forward reaction. Okay, so this is a one-way reaction. One-way reaction. And so I'd like to set everything up in ice tables for Chem 1b. And so starting off with the HCl, we have 1 times 10 to the minus 8 molar. HCl is pure liquid. And then we assume nothing is hydrolyzed yet. And so I just have that. And then we know that this is a strong electrolyte. We're going to lose all of it. 1 times 10 to the minus 8. That is, we're going to have complete hydrolysis or complete dissociation into. We're going to get plus 1 times 10 to the minus 8 molar and plus 1 times 10 to the minus 8 molar here. And so at the end of this, we're going to have 0 molar. That is, it's all gone. And we're going to get 1 times 10 to the minus 8 molar, 1 times 10 to the minus 8 molar here. And so in step 1, how much hydronium did we produce? We produced 1 times 10 to the minus 8 molar. But if we stop here, we're not getting all the hydronium in the solution because there's a step 2. And step 2 is going to produce a little bit of hydronium as well. That is H2O liquid plus H2O liquid. This is going to go to hydronium plus hydroxide. This is KW, and KW, you can't stop the collisions. So even if we're dealing with hydrochloric acid solution, the water molecules are still colliding with one another and generating hydronium and hydroxide. Not much, because KW is not very large. KW is very small, 1.0 times 10 to the minus 14. Most people memorize this, KW of 25 degrees C. 1.0 times 10 to the minus 14. Okay, there's a common species. What's the common species between these two? Hydronium, right? And so this is it's an ion, and so we call it a common ion. And so this is what we call a common ion type problem. And so what we're going to do is we're going to take the hydronium from step 1 and place it down here. So this is going to be 1 times 10 to the minus 8 molar. Now, initially, we're going to say that the water has not reacted with itself. It hasn't collided yet. And so we're going to just say 0 molar. There are two choices that we can do here. We can say that the water has already reacted with one another. That's going to form 10 to the minus 7 molar and 10 to the minus 7 molar, and then add this. But the problem with doing that is it makes the calculation more difficult. So the best thing to do is reset it like this. If we reset it, it'll make the calculation a lot easier. And that is, we reset it to the left. That is, we assume nothing's happened, and then we add plus X molar here. And so at the end of this, we're going to have 1 times 10 to the minus 8 molar from step 1, plus X molar from step 2, And so if we do that, then what we're going to get is we're going to get the total hydronium here in the mixture. Okay, and then the hydroxide. If you think this is an acid solution, so why should we have hydroxide? Well, we're going to have hydroxide in any solution, whether it's acidic, basic, or neutral. There's always hydroxide present because you can't stop the waters from colliding. And so how do we define what an acid is and how do we define what a base is? It's the way we define it is if the hydronium concentration is greater than the hydroxide concentration, then it's an acid. If the hydronium and the hydroxide concentration are equal, then it's neutral. And if the hydroxide is greater than the hydronium, we call it basic or base solution. It's a base. And so, we're always going to have hydronium and hydroxide present in all solutions because we can't stop the waters from colliding. It's just how much do we generate? Now, acid solutions are going to have more hydronium, so this is what we're going to see. We're going to have the hydronium produced from the acid, step 1, plus any additional hydronium from step 2, which is going to be the KW here. And so let's solve for X. Here. So we solve for X. KW is going to equal the hydronium times the hydroxide, which is going to equal 1 times 10 to the negative 8 plus X times X. Okay, one thing is I don't expect X to be very big. I expect X to be small because KW is so small. This heavily favors the reactants, so the water. And so I expect very little. So I'm going to try the simplifying assumption. If I try the simplifying assumption, this is just going to equal 1 times 10 to the minus 8, and the X is negligible, and that leaves that X. So this is the simplifying assumption, which gives me an X value. X is equal to 1.0 times 10 to the negative 6. So if the change is 10 to the minus 6, and our initial is 10 to the minus 8, what was the percent change? Well, the percent change is going to be 10 to the positive 2 times 10 to the, it's going to be a 1,000% change. Well, 1,000% change is much greater than 5%, so this failed. The reason it failed is not because of X being too big. X is very small. It's because our initial is so small. we're saying that X is negligible compared to our initial. And so this is like, if you take a drop of water and add it to a swimming pool, did the swimming pool volume change much? No, it's a negligible change. But we're not adding it to a swimming pool. We're taking a drop of water and adding it to a half a drop of water. If we take a drop of water and add it to a half a drop of water, then it's changed significantly. And so that's kind of what we're saying here. And so it failed. If it fails, then, well, the math is not too bad. It's just quadratic. So let's go ahead and get it in quadratic form. And then calculate it. And so SA failed. And so let's get it into quadratic form here. And then just use the quadratic symbol. One thing I didn't realize, well, actually, I always wondered about this, but some of these quadratic solvers, what's the programming that goes into it? And when we're working on some problems yesterday, we realized that it gave the wrong answer. And so you have to worry about these quadratic equation solvers here. The calculator does pretty good. And so if you get like the Casio, I haven't had any, or haven't had much problem with those. But let's try this quadratic solver here. 1 comes to 14. Solve that. So this is pretty good. The one that the solver can solve, I used. Are you familiar with this program? Wolfram Alpha. This is pretty powerful. So you can plug in a quadratic in here and solve it, like this quadratic here. And you get the solutions here. So Wolfram Alpha is a good option to do as well. That works for homework, but you can't use the Wolfram Alpha or the quadratic solver online for this test. Now anyway, we come up with X is equal to 9.51. The other one's negative, so we can't have negative concentration. So it's going to be 9.51249. We'll just carry this. This is overkill. Times 10 to the minus 8. Times 10 to the minus 8. I just worry about round off error. That's the reason I carry so many digits. And so what we're going to get is we're going to get the total hydronium concentration, which is going to be here. Let's go ahead and calculate that. Total hydronium concentration is equal to the hydronium from step 1, 1 times 10 to the minus 8, plus the hydronium from step 2. The hydronium from step 2 is 9.51249 times 10 to the minus 8. So this is going to be plus 9.51249 times 10 to the minus 8. And so we're going to get a total hydronium of 10.51249 times 10 to the minus 8 molar. So when we look at this particular problem, which step contributed more hydronium? Step 1, 10 to the minus 8, or step 2, 9 times 10 to the minus 8? Step 2 contributed almost 10 times more hydronium to this than step 1. And we're also going to form some hydroxide here. How much hydroxide are we going to form? We're going to form 9.51249 times 10 to the minus 8 molar hydroxide. All right, let's go ahead and check our K value to make sure that we didn't make any errors here. And so we're going to take this one, 10.51249 times 10 to the minus 8 times 9.51249 times 10 to the minus 8. And what do we get from that? And 1.0 times 10 to the 14. And so it checks out. That's good. Okay, now we want to calculate the pH. The pH is equal to the negative log of the total hydronium. Well, what is the total hydronium? The hydronium is going to be the sum total of step 1 and step 2. And so this is going to equal the negative log of the hydronium from step 1. I'll just write it out like this. Plus the hydronium from step 2. And we already did that calculation. And so this is going to be the negative log of 10.51249 times 10 to the minus 8, which is going to give us a pH of 10.51249 times 10 minus 8. Take the log and then change the sign to 6.978. So this gives us a pH of 6.978. And then how many sig figs am I allowed? So I only have 1 sig fig here in the concentration. That translated down to here. And then here I'm going to have 2 sig figs. So I'm going to have 2 decimal places. Here I have no decimal places. So I'm going to have 2 sig figs here. So I'm allowed 2 sig figs in my pH. This is going to come out to 6.98. 6.98 is below 7. So if we're at a pH of below 7, that's acidic. This is acidic. But I also said that, I would drink this. I would drink this. Why? Because it's almost like drinking pure water. Pure water is pH 7. And so this is just slightly acidic, almost neutral. The tap water here is like pH 4.5, I think. pH 5, which means this is a lot more acidic. So this will be close to distilled water. Just very slightly acidic. All right, so the stepwise work here. The stepwise fails sometimes when this happens. Sometimes fails if, let's say, if a step perturbs the previous step. Perturbs previous step. Then can fail. So what do I mean by that? What I mean by that is Le Chatelet's principle. This is Le Chatelet's principle. With Le Chatelet's principle, we're in step 2. We're increasing it by about 10 times. You see, in step 2, we have 10 times more hydronium. So let's go back to step one. If we go back to step one here, what happens if I increase the hydronium? So I went from 1 to 10. And so I have 10 times more hydronium. If I increase the concentration by a factor of 10 here, which direction does the equilibrium shift? It shifts to the left. And so what we should see here is that step 2 perturbs step 1 because it's going to force step 1 to shift to the left because now we have a lot more hydronium. It's both step 1 and step 2 are in the same solution. So they're both going to have the same hydronium because there's no difference. We can't isolate step 1 separately from step 2 because they're both happening in the water. But the reason it doesn't perturb here is because this is a one-way reaction. When K is very large, then it's not perturbed by Le Chatelier's. So this means this is not perturbed by Le Chatelier's. Another way we can think about this is chloride. If I add lots of chloride, we expect it to shift to the left if I add lots of chloride. So if that's the case, then chloride will, if I add lots of chloride will decrease the hydronium, right, as it shifts left. So the more chloride I add, the less hydronium I have because we're going to go backwards. And so that's going to reduce the hydronium and increase the pH. So would chloride work as an antacid? So let's say you ran out of antacid and you have table salt. And table salt has chloride. So can you eat lots of salt and expect your stomach acidity to go down? That is, the pH to go up, the hydronium concentration to go down. So in other words, I'm going to use chloride to Le Chatelier shift this back to the left. We have HCl in our stomach. I don't want as much hydronium. I want to increase the pH. So will eating lots of table salt decrease the hydronium, increase the pH? And the answer is no, it has no impact. So if I increase lots and lots of chloride here, there's no impact. It's going to be completely ionized. It's not going to revert back to molecules here. And so what we say for this particular problem is that step 2 does not perturb step 1. We can't perturb step 1 because it's a strong acid. Strong acids have a K that's very large. That K that's very large results in a one-way reaction. You can't go backwards in this particular reaction. And therefore, it's not going to be perturbed by Chatelier's, which means we don't have to worry about having to do simultaneous, which is the harder method here. Of course, we could solve these simultaneously, but not bother, because even if we solve these simultaneously, we're going to get the same answer. So that takes care of this. So we get an acidic solution. It's just not very acidic, but at least it's not a basic solution. Okay, let's do an example of a simultaneous. The simultaneous one we'll look at is going to be 1 times 10 to the minus 8 molar HCN. Let me bring this up here. And what we want to do is we want to figure out what the pH is equal to. Okay, but when we look at the K for HCN, hydrocyanic acid, here, K is 6.2 times 10 minus 10, which is quite small. And so we went from very large to something that's pretty small. And so what that says is that HCN is not a very strong acid. So, but it's stronger than water, so let's start off with HCN. So we're going to have HCN. There are going to be two contributors to hydronium. One, HCN, two, water. And so we start off with step one. Step one is to figure out how much hydronium we get from acid hydrolysis. Okay. Acid hydrolysis or acid ionization is Ka. So how much hydronium do we get from Ka? Okay, since this is not a strong acid, we can't assume complete hydrolysis, complete ionization, and we'll have to calculate it. Well, how much is it? Well, we don't really know just yet. And so initially I start off with 1 times 10 to the minus 8 molar HCN. Water is a pure liquid like that. And then we assume that nothing is hydrolyzed yet. And so there's no hydronium or no cyanide initially. And then we let it hydrolyze. So we'll lose a little bit, minus X, not much because this is so small. We'll get plus X molar here, plus X molar here. And so at equilibrium, we're going to get 1 times 10 to the minus 8, minus X molar, and X molar. Now Ka is very small. And so that's good. The change should be small. And so Ka is going to equal the hydronium concentration times the cyanide concentration divided by the HCN concentration here. So this is going to equal X squared over 1 times 10 to the negative 8 minus X. We can try to simplify something here. You know, normally I just try it because it doesn't take too much time. But I have a suspicion it might fail here. The reason it might fail is because the initial is so small. It's not like removing a drop of water. If you remove a drop of water from a swimming pool, there's barely any change. It's will become negative change. But 10 to the minus 8 is not exactly a swimming pool of concentration. You know, this is more like the damp napkin, not even a damp napkin. But anyway, what we're going to do is try it anyway and see what happens. If we try the simplifying assumption and just see what happens, then this is going to simplify to X squared over 1 times 10 to the minus 8, which is going to give us, well, let's see what the calculation comes out to. So I'm going to get 6.2 times 10 to the minus 10 times 1 times 10 to the minus 8. Actually, I should have been able to do that. 6.2 times 10 minus 18, and then take the square root of that. I'm going to have 2.4 times 10 to the 3, 6, 7, 8. 2.4 times 10 to the minus 8. Which is going to be a 240% change. 240% change is much larger than 5%, so this is not going to work for us. So the simplifying assumption fails. And it's not because the change wasn't small. The change was small. I mean, it's 10 to the minus 8. It's just we had so little to begin with. The change is significant. So we're going to have to use the quadratic. That's fine. So let's get this into quadratic form. So quadratic form is going to be x squared plus 6.2 times 10 to the minus 10 x minus 6.2 times 10 to the minus 18 is equal to 0. All right. Let's try the quadratic solver. This is one on a different site here. We have one. So there's a choice of quadratic solvers you can use. 6.2 times 10 to the minus 10. Next one is going to be negative 6.2 times 10 to the minus 10. Oh, 10 to the minus 18. Let's calculate that. So I get an x value equal to 2.1992 times 10 to the minus 9. X is equal to 2.1992 times 10 to the minus 9. All right, let's plug that in here and let's see. Okay, if that's 10 to the minus 9, we'll make this bigger and the coefficient smaller. So we're going to make this 10 minus 8, so it's going to be 0.21. And so this is going to equal 1 times 10 to the negative 8 minus 0.21992 times 10 to the minus 8, which is going to give us 0.7. Eight. 008. All right. Check that. 1. Yeah, that's right. Times 10 to the minus 8 moles. Okay, this is going to be 2.1992 times 10 to the minus 9 molar, which is going to be the same as this. All right, let's double check our K value to make sure it's correct. So the K is equal to the hydronium times the cyanide. So I'll just take 2.1992 times 10 minus 9 square that. 2.1992 times 10 to the minus 9. Square that. And then divide it by the HCN concentration, which is 0.78. I get 6.199 times 10 to the minus 18. Right? Well, let me double check that because it should be 10 to the minus 10. We must have made a mistake somewhere. Let me do this calculation here. So 2.1992 times 10 to the minus 9 squared divided by 0.78008 times 10 to the minus 8. Oh dear. 2.1992 times 10 to the minus 9 squared divided by 0.78008 times 10 to the minus 8.
I got 6.199 times 10 to the negative 10.
Okay, good. So we should have gotten it. Thanks. So this comes out to 6.199 times 10 to the negative 10, which means it's good. Right? It should be 6.2. That's what it came out to. All right, so we're going to get some hydronium from the acid, but we're also going to get some hydronium from water. And so that's going to be our step 2. KW. So step 1 was Ka acid. So how much additional hydronium? Not much. I mean, the most hydronium we get is in pure water, which is 10 to the minus 7. We're going to get less than that, but it could be significant in this particular problem. So what we're going to do is find out how much plus hydroxide. And so the common species between these, in other words, the common ion, this is a common ion problem, is hydronium. So we're going to take the common ion from step 1 and then start with that in step 2. And so that common ion here is 2.1992 times 10 to the minus 9. And so initially, I'm going to have this hydronium, and the hydroxide is going to be 0 molar. And then how much additional hydronium I'm going to get? So what I'm assuming is nothing's reacted. Yeah. We already know in pure water there's already hydronium. It's 10 to the minus 7 molar. But this is an easier way of solving it, because if we start off with 10 to the minus 7 molar and 10 to the minus 7 molar, it makes it more difficult because then we Le Chatelier shift it back left, and it's just much easier just assuming nothing's happened with the water and then start it with the common ion only. All right, then we'll let the water hydrolyze, and so we'll get plus X molar and plus X molar. Now, X is not going to be 10 to the minus 7 because we don't need to produce as much product when we already have product there to begin with. So this is called the common ion effect, or Le Chatelier's principle. Le Chatelier's principle says if you increase the amount of hydronium, you shift it left. And so that shift left means we're going to get less forward reaction. And so at equilibrium, I'm going to have the hydronium from step 1, which is 2.1992 times 10 to the minus 9, plus the hydronium from step 2, which is just added. And then I'm going to have this X here for the hydroxide. All right, so let's go ahead and do the calculation here. Kw is the hydronium times the hydroxide. And so this is going to be 2.1992 times 10 to the minus 9 plus X times X. This is equal to 1.0 times 10 to the minus 14. All right, so when we do this here, we'll see that on the one hand, the simplifying assumption should work because it's such a small k. With such a small k, 10 to the minus 14, we don't expect much forward reaction, so X should be very small. On the other hand, the simplifying assumption should fail because our initial amount of hydronium is so small that any change would be significant. But we can just go ahead and try it. If we try it, then this is going to simplify to 2.1992 times 10 minus 9. The X we're assuming is small, that it's negligible, times X. And so X is going to equal 1 times 10 to the negative 14. 1 times 10 to the negative 14 divided by 2.1992 times 10 to the negative 9. 2.1992 times 10 to the negative 9. 4.54 times 10 to the minus 6. 4.54 times 10 to the minus 6. So our initial is 10 to the minus 9, our change is 10 to the minus 6. 10 to the minus 6 is 1,000 times bigger, so our change is 1,000 times bigger than our initial. And so that means our percent change is going to be 100,000%. 100,000% is too big. It's much bigger than 5%, which are cut off, so this fails. Unfortunately, the simplifying assumption failed again. And therefore, we're going to have to use the quadratic formula. So let's go ahead and do that. So this is going to come out to x squared plus 2.1992 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. So let's solve for x here. So a is equal to 1. B is equal to 2.1992 times 10 to the minus 9. 2.1992 times 10 to the minus 9. C is equal to negative 1 times 10 to the 14. I guess I already have that there. Let's calculate that. Can't be negative, so we'll take the positive. 9.89 times 10 to the minus 8. So I'll try some more extra digits to avoid rounding error. 9.89064. 9.89064 times 10 to the negative 8. All right, let's go ahead and plug that in here. So this is 10 to the negative 9, so I'm going to make this 10 to the negative 9. So if I make this 10 to the negative 9, I'm going to make the protein bigger. And so the amount of hydronium originally was 2.1992 times 10 to the minus 9. And then in step 2, we're adding some additional hydronium to that. And so it's going to be plus 98.9064 times 10 to the minus 9. And so the total hydronium here is going to equal 2.1992 plus 98.9064, 101.1056. So the total hydronium here is going to be 101.1056 times 10 to the minus 9 molar. And the hydroxide here is going to be 9.89064 times 10 to the minus 8 molar. Okay, let's check K to make sure we didn't make any calculation errors. And so I'm going to take 101.1056 times 10 to the minus 9 times 9.89064 times 10 to the minus 8. And that checks out. And so when we check K is equal to 1.000 times 10 to the 14. So it's good. So we can see here that step 1 contributed 2 times 10 to the minus 9. Step 2 contributed 50 times more, almost 100 times 10 to the minus 9. And so step 2, water was a significant contributor to the hydronium, even though the K is pretty small. The reason is because even though this K is bigger, we just didn't have very much. There at the beginning. And so we went from about 2 to 100. Well, now what we have to do is when we do this, we did this stepwise. Whenever we do a stepwise problem, we have to make sure that this step, step 2, did not perturb step 1. And so when I do that, I look here at, let's see, I look here. This is my new hydronium. Both step 1 and step 2 are in the same beaker, and so there's only one hydronium. For example, we cannot isolate step 1 from step 2 because the water and the HCN are in the same flask or same beaker, and there's no way to have hydronium that's reserved for HCN and hydronium that's reserved for water, because the hydronium is free to go anywhere in that beaker. And so this is the new hydronium. Well, the new hydronium is different than the old hydronium, so we have to see. The old hydronium was 2, and we no longer have 2, because we just added 98 more. And so the new hydronium from step 2, the total hydronium now is equal to 101.1056 times 10 to the minus 9 molar. So if we change this here, the cyanide is going to remain the same, because that didn't change from step 2. The cyanide stays at 2.1992 times 10 to the minus 9 molar. But the hydronium did change. Is K still going to be correct? Well, for one thing is, if we increase the hydronium, what's going to happen? It should shift to the left. And we will see it should shift to the left, because if we try to calculate K again, K is going to be the new hydronium, which is going to be 101.1056 times 10 to the minus 9, times the cyanide, which is going to be 2.1992 times 10 to the minus 9, divided by the HCN, which is 0.78008 times 10 to the minus 8. But what does K come out to now? So do that calculation. 101.1056 times 10 to the minus 9 times 2.1992 times 10 to the minus 9 divided by 0.78008 times 10 to the minus 8. 2.85 times 10 to the 3, 6, 7, 8. This comes out to 2.85 times 10 to the minus 8. 2.85 times 10 to the minus 8 does not equal 6.2 times 10 to the minus 10. And so it's no longer at equilibrium. And so what happened is step 2 perturbed step 1, so now that step 1 is no longer at equilibrium. And so what's going to happen is step 1 is going to have to shift left. And that means we have to calculate new concentrations for step 1. So if we go back and set up a new ice table, we call this step 3, and then we shift this to the left, what do you think is going to happen to step 2? So in other words, we did step 2, step 2 comes out right, so we go back to fix step 1. After we fix step 1, what do you think is going to happen to the hydronium? It's going to perturb step 2. So what we're going to end up doing is we're going to be in circles. So we do step 1, step 2, and then step 2, and then step 2 screws up step 1. So we go back to step 1, fix that, and that screws up step 2. And so what happens is this becomes impossible. Impossible to solve stepwise. And so in Chem 1B, you just have to recognize when stepwise fails. If stepwise is working okay, then that's great, then you check it. But if you recognize that stepwise fails, then you have to say or make note of it. So here, stepwise failed. must do simultaneous. All right, so how do we do this simultaneously? Let's try that out. So we're not going to do one and then the other. What we're going to do is we're going to do both together. And so how do I set up both together? It's a little bit weird conceptually, but kind of makes sense. So let's look at an example. This will be simultaneous. So we solve both together, so we'll put HCN plus H2O, liquid. This goes to hydronium plus cyanide. And then the other one is going to be H2O liquid plus H2O liquid goes to hydronium and hydroxide. All right, so initially we have 1 times 10 to the minus 8 molar HCN, water is a pure liquid. And then what we're going to do is we're going to assume that water's already contributed some hydronium. Now, how much hydronium are we going to get from water? I'm just going to call that Y molar. This is from H2O. KW. And we're going to assume that the HCN has done nothing yet, 0 molar. So water's already done its thing and generated some hydronium. And what we're going to do is we're going to figure out how much additional hydronium we're going to get. So this is going to be minus X plus X molar plus X molar. So this is a common ion type problem here. We're going to not generate as much because of the presence of initial amounts of product. Y plus X molar. X molar here. So the total hydronium will be the hydronium from KW and the hydronium from Ka. Ka being the acid here. Okay, at the same time we're doing this, we're going to go back to the water here. And we have initially water is pure liquid, so we can omit that. But this is going to be kind of weird. What we're going to do is we're going to go here to water and assume that nothing's happened with water, but Ka is already taken place. That is, we already have hydronium from HCN. Now, how much hydronium did HCN generate?
Water plus X.
Well, Y plus X is the total hydronium. So Y plus X is the hydronium from the water, KW, and the acid, Ka. The actual amount of hydronium that the acid generates is just X. And so we're going to assume that we already have some hydronium from the acid here. That's our X. But we're going to say that nothing's happened with water yet. And so this is weird because now, earlier we were saying that water's already reacted and nothing's happened with HCN. Now we're going to do the opposite. We're going to say that nothing's happened with water, but it's already happened with HCN. So both can't be true, but that's the way we're going to solve this. Then we're going to let water hydrolyze, and then we're going to get plus Y. and plus Y molar here. And so we already have some X molar from the acid. So this is common iron from the HCN. Ka. And so at equilibrium, we're going to have X from the acid plus Y from water molar, and then Y molar. And so this is in the same solution. You know, we can't separate the HCN or isolate it from the water. They're all together. If they're all together, then they both simultaneously have to have the same hydronium concentration because there's only one hydronium concentration in the beaker. And so this is why they come out the same, Y plus X, X plus Y. Well, we have two unknowns here. If we have two unknowns, we're going to need two equations to solve that. And so what are the two equations that we're going to generate? Well, the first equation is going to be the Ka equation. The Ka equation is going to be the hydronium times the cyanide. So this is going to be Y plus X times X divided by the HCN, 1 times 10 to the minus 8 minus X. Okay, and then the other equation that we're going to have is Kw. Kw is going to be X plus Y times Y. And so how do you solve a system of equations like this? You usually solve for one variable and then substitute. Yeah. But this one's a bit more tricky. You know, even though it seems pretty simple, you just solve for one and then substitute to solve for the other. It's not so easy. And so, what we're going to do is it. Let's take a look. So in this box 16.1, are you wondering, okay, you know, how do we calculate hydronium in an extremely dilute solution of a strong acid? Well, that's what we just did. In fact, they use the same. I use the same. 1 times 10 minus 8, except they use 2 6 because I use 1 6 there. What your book often does is they'll skip all the ice tables. So here they skip step 1. They use 1 straight to step 2. You see that? And this is step 1. From step 1 we got this, and then we add some from step 2. So step 1 plus step 2. So they don't set up the ice table. I think it's just to save space. And then they use the quadratic to solve it. Okay, in 16-2, are you wondering? Here they're doing this very dilute solution of weak acid. When we have a dilute solution of weak acid, then stepwise fails. You have to do it simultaneously. There are other scenarios. This isn't the only scenario that we have where stepwise fails. And so just in general, we need to know when stepwise fails. Well, anyway, they're going to solve this simultaneously. So they didn't set up the ice tables. I set up the ice tables here. They just skip the ice tables entirely and just go straight to the equations. And so they come up with these equations here, except when they solve, they don't solve for x or y, they solve for x plus y and then substitute that into kW. But even if you solve for x plus y and substitute that into kW, we know what C is. C is the initial concentration. They didn't give us the initial concentration. I use the initial concentration 1 times 10 minus 8, so that would be that. And therefore we only have one ml here. But solving this kind of equation is mathematically it's pretty tough. Do you see that? What order is that? Well, this would be x to the minus 1. This would be x squared or x on the top. So this would be a tough equation to solve mathematically because it looks, well, maybe not. I don't know. It just looks tough. You could try solving it. So they picked a concentration here for 1.0 times 10 to the minus 5 molar HCN. I use 1.0 times 10 to the minus 8 molar HCN. The same kind of thing. And then I substitute the Ka value here and the initial concentration here. Well, we've already done that in the equation above and solve for x. But solving for x isn't so easy. Here they're using the method of successive approximations to solve for x because the algebra isn't so easy. See Appendix A. And so what this means is that and so for this class, you have to recognize when it's simultaneously. And you could get it like set up like this, but you don't have to solve as for x and y. Because it's a lot of math. Not as much Chem, I guess. Although we've already done successive approximations. Solve for x and y. This would be like bonus points. And so up to here, this is fine for Chem 1B. But this would be like extra credit. I'm not going to solve it. You can look at box 16-2 if you want to work on solving it. Since we need some bonus for simultaneous reactions. Okay. Let's look at some other stepwise problems. Another stepwise problem would be something like phosphoric acid, H3PO4. Phosphoric acid is a triprotic acid. HCN is a monoprotic acid. And so when we think about all the hydronium producers here, it's an acid solution. So we're going to get hydronium from HCN, and we're going to get hydronium from water. Over here, it being a triprotic acid means that we're going to get hydronium from the first hydrogen that breaks off. And when we look at that, it produces hydronium and dihydrogen phosphate. The Ka1 means step 1 of this acid is 7.1 times 10 to the minus 3. We're also going to get hydronium from the second proton breaking off. So dihydrogen goes to monohydrogen, that's 6.3 times 10 to the minus 8. So it's much weaker. So the first one's the most acidic. The second one's about 10,000 times weaker. It's 5 orders of magnitude. And then the third acid, hydrogen, breaks off, giving us phosphate. and that's going to be 10 to the minus 13. So that's another 5 orders of magnitude, or 10,000 times weaker. And this is good for stepwise. What we wanted to see is that each successive step produces less and less. If that's the case, it's less likely to perturb the previous step. And so in step 1, we're going to produce the most. In step 2, we probably produce negligible, and then step 3, even less significant portion. And so when we have this scenario where Ka1 is much greater than Ka2, which is much greater than Ka3, then we can do this stepwise, step by step. There are scenarios where that's not necessarily the case here. And so let's look at some of these here. This is fine stepwise too. Because if we look at K1 is 10 to the minus 7, K2 is 10 to the minus 19, that's 12 orders of magnitude difference. So this step should barely produce any compared to the first step. Carbonic acid, 10 to the minus 7, 10 to the minus 11, that's pretty good candidate for stepwise. Citric acid, maybe not such a good candidate, because here step 1 is 10 to the minus 4, but step 2 is 10 to the minus 5. That's not that big of a difference, just tenfold different. So I would start to worry about citric acid, step 2 producing significant quantities of hydronium, which perturbs step 1. Step 3, not, well, 100-fold difference. Here's phosphor. This is good, 10,000, 10,000, 10-fold. Oxalic is good 1,000 times. Different. Sulfurous is good. That's 1,000,000 times difference, 10 to the 6th. Sulfuric acid, now, this is tricky because the first step is very large. That's 100% complete. When we see very large. The second step is 10 to the minus 2. Now, 10 to the minus 2 is pretty big, significant. And so here, we produce most of the hydronium in step 1, but we add another about 10% from step 2 because this is kind of large. Here. And so if you look here in step 1, this is 10 to the minus 2. This is in step 2, this is 10 to the minus 2, which is kind of big. All right. So let's take a look at phosphoric acid here. Let's see how much time. We're out of time? Oh yeah, we're out of time. My watch died. So let's see it. All right, we'll look at phosphoric acid on Wednesday. Now tomorrow's lab is going to be a pH titration, so I'll talk about the lab at the beginning. I'll send it out to you and then we're going to go through it in detail tomorrow. I was going to talk a little bit about it today, but it's all right. And so just scan through the lab. You can prepare your notebook if you wish, but if you don't, that's all right since we're out of sync with it. Okay, let me So just scan through the lab or read through the lab, and then